I really like it, but it's really hard.
Yeah.
To figure out what's going on in the
Yeah.
class.
Well, it's just like we only do cases, so like don't ever do anything theoretical. And so he teaches like everybody's investment banking status. Yeah. Like he'll find problems, and John McGee is like, I don't know.
Really?
Yeah.
John?
Yeah. When like you passed all 3 levels of CFA exam and you're confused. Yeah.
Well, at least there's the beautiful thing with the curve.
Oh, that's what I'm living on right now. Absolutely. Yeah.
Oh, they just took transgenders bathroom? Scrap that whole transgender
Yeah, she
stuff.
lives on.
Yeah, that's over.
I keep want to say Natalie,
read-
but I
review
forget
that.
that
Don't
she's
call her
from
that.
East. Yeah, I think she's from
So whatever
Eastern
you're
Europe.
born with,
Yeah.
stick with it.
Well, if you want to upset her real quick, just be like, Natalie,
Yeah,
what's
yeah.
going on? She gets so mad.
I
Yeah.
need to remember that it's European since Natalia.
Of course. There you go. Well, then what's weird is so her last name is Bargova, but her dad's name is Varga. Because in the Czech Republic, you for females, you have Ova.
Oh,
Can't go
really?
into a woman.
Blew my mind. Yeah. I was like, your parents.
So where the guys go.
I had no idea. I had no idea.
Cut that out.
Yeah.
And my neighbor said,
Oh my God, spectacular.
my
Yeah, we
neighbor
went
said
to a
to me,
romantic
well,
Taco Bell dinner on
get ready.
Monday night.
there'll be a lot of
Doesn't get better.
Fajita.
Cheesy Rita Crunch, dude.
you can buy in another year or two.
We've looked into it. There's a contest,
For
and
instance,
then if you win the
a lot of,
contest, they waive the $500
Latino
fee.
in my-
I might have signed us up.
in my area.
If we win, I don't know if she'll go for it, but I want to go for it.
And the dogs, the past it.
Yeah, I think that would work.
You can think that.
Oh well, they'll never. They don't listen to us, so I can't trust any of those dogs with a ring or anything.
So we'll see. We'll see what it's all about.
Mike, how we hanging over there?
Dude, I'm great. How are you, bud?
Good.
You're trying to look better than me every day because it's working. You used to always look good. What do you got going on?
Case got something with I'm on John McGee.
Oh, cool.
The AC, it was like investment banking type.
Oh, gotcha. I heard that thing's a nightmare. You guys with pop?
Yeah.
Yeah.
I mean, it was a lot of work, but it was, we also did more work than necessary. It's banking.
Oh, yeah. Wham, those guys. Yeah. Yeah. Oh, John McGee is like the most detail-oriented human I've ever met in
Well,
my
it
life.
was actually,
What is this? Actually, it has the cover.
it was,
Cover your. So you like this?
Yeah.
So you like.
I gotcha.
it was actually Pav. Pav like, ran a lot of it.
See if it works.
Really?
Yeah. Yeah, he's, Pav's,
Oh, sorry. That's fine. I made myself out back here. Sorry about that. Yeah. Oh, I know one for like the UCLA stock competition or whatever. Pat was telling me he was trying to run a regression on how weather affects people going to SeaWorld. And I was like, you're out of your mind.
Or how certain movies affect whether people go to SeaWorld, that's another one.
Well, no, you don't do a regression on that. It's 100% you stop going to SeaWorld.
Yeah, exactly.
Dude, that movie's
Blackfish
crazy.
and
Such a crazy movie.
I know.
Yeah. At the same time, whatever human wants to get in a tank with a killer whale, you're out of your mind.
Yeah.
It's not a good idea.
It's just like, yeah, safe distance, you know?
Absolutely.
Flung in the air, you know?
How's it going over there?
Oh, no, it's fine.
Oh, it's like it covers my webcam.
No, I'm seeing my. I know you, so.
For having you, I didn't know I still sold those.
I,
That's fantastic. Dude, that whole case on Tesco is gonna be so hungry. Have you been to a Tesco before? Or Fresh and Easy? Yeah. I've been there once before.
Oh man, I have another.
Yeah, oh,
string
100%.
going through
Yeah,
that
it's like
last
all
class.
white marble, like, yeah, like yellowish
Spending
lighting.
a lot of time trying to.
You walk in there like, what?
I can't
Most of the day I want to talk about this log normal model for stock prices.
And yourself?
And that's actually not quite true because I said most of today, but I actually kind of want to split it, and I want to start out and finish the in-class exercise we did last week on the Pareto distribution, and then go on and talk about your homework and the log normal model a bit more. So let's start about finishing this in-class exercise. And I thought the easiest way was to actually post my Excel file so that I can just kind of make sure we're all on the same page. So I posted my Excel file. And before we go there, I want to just talk a little bit about the Pareto distribution because I think it's an interesting distribution and I want us all to be on the same page for why it's something we might care about. And for some context, so the first part, what we were doing in that in-class exercise, the overall picture was basically you have a data set, you've done some histogram plots, you've done some initial tests, you've decided to represent it with a Pareto distribution because you've decided that some of the outliers in the data set are important and you want a distribution that is genuinely going to model these outliers, you don't want to drop them. And so then we need to figure out what should be the distribution parameter. And I felt like Pareto is a little bit new, and it was coming up in this in-class exercise, so I'd like to say a little bit more about what it is so we can just kind of all have a good intuitive feel for what is Pareto distribution. So when is it coming up? You've got a data set with a very few large observations, and you don't want to drop the large observations. You think they're genuine, so you genuinely want a distribution that models some of these large observations. And why do we care about this distribution? So I thought I would try to think of an example in the news that sort of makes use of this distribution. Do you remember the Occupy movement? Can somebody connect Occupy and Pareto for me? The 1%. Yeah. Okay, so we got some outlier observations of people with really large wealth, and that's not something we can just drop and ignore. And so Pareto might be useful to model that. And that's, of course, exactly what the occupier people were upset about. A few people controlling a very large percentage of the wealth. So that's basically the idea of situations when the distribution arises, or when you have a few people or things or whatever accounting for a large proportion of the population. So why don't you tell me a few other examples where this distribution might be of interest? Sales, and I think in particular some businesses will say that a small percentage of the customers are actually making up a large percentage of their revenue. JP?
This is actually kind of coming from a public transit perspective. Basically, when you're modeling transit ridership, most authorities generally find that about 80% of your ridership comes from like 10 to 20% of your routes on buses.
Yes, I like this too, and this 80-20 rule is coming from a Pareto distribution with a specific parameter. Louis?
Yeah, it could be like the mass of a solar system. So like 99% of the mass of the solar system is located in the sun, but that is only one object compared to the billions we have.
Yeah, I hadn't thought of that one. I like that. So one object is the really large mass.
In my last shot, we did a lot of like IT service ticket analysis, and we're finding that for going to have lower average to like respond and resolve times, that there's a lot of those averages were driven up by like 1 or 2s that maybe some of the ticket had been left open like for months, but it was closed that month, therefore got.
Oh, that's a good one. So it's like a couple of the customers generating really long response times.
Yeah.
Right?
In real estate, if you're trying to find the average home price and you're looking in a city in which maybe Bill Gates has a $50 million home, and all the other homes are $1 million, he's going to skew it, so.
Yes, definitely. And another one I thought of was insurance industry. Sometimes you get a few claims that are responsible for a large proportion of the money that has to go up. Okay, so the point is there's several situations where this type of distribution is interesting to have in your toolbox. And hopefully I've convinced you of that, because let's think a little bit about what that parameter D in this distribution is doing, and why do we want to fit that parameter D. Okay. So these are pictures of the distribution. And let me start with the CDF, right? So the way we're reading the CDF, I've plotted the CDF for different values of this D. is the parameter that's determining which Pareto distribution do we care about. And I think the thing to observe is, let's look at like the value 2. So if I think about the probability that your data, the probability that you get a value less than or equal to 2, that's what the CDF is telling me. And you can see that that probability is much lower when D is small than when D is large. And that continues out. So if I look at a value like 5, for these values of D that are like 2.5 and 3.5, basically all of the values of the distribution, say at least 99%, are occurring between 1 and 5. But when D is down here at 2.5, it's, I don't know, maybe only like 5% of the values. And when D is down here at 0.5, it's maybe only like 55% of the values. So D is really controlling what is the probability that you're going to see outlier observations. If D is larger, I'm not seeing any outlier observations in these distributions, right? They're all kind of less than 5. But, you know, if D is smaller, it suggests, you know, there seems to be a non-trivial probability of having some larger stuff. You can also kind of see that by looking at the PDF, but it's a little bit more subtle. So if I look at the PDF, this is kind of telling me the relative frequency that values occur. So low values, this D at 3.5 is higher. Low values are much more likely to occur under a high D. But let me blow up this plot a little bit. So let me blow up that axis out to like 100. And, you know, now I'm getting really small values. But even though I'm getting really small values, you can see that for low values of D, I'm relatively much more likely to have a large observation under a low value of D than a high value of D. I mean, they're never going to be very likely, but they're sort of much more likely if D is small. Does that make sense? So if I'm having this data set and I'm caring about fitting this sort of tail portion, what I really care about is getting the value of D correct. And we saw this a little bit, because if you think about how we ended class last time, we made this observation and we said the sample mean of the data set is 606 seconds. I gave this to you. The sample mean of the Pareto is determined by this D. So now you have a little equation you can set up and you can solve for D, and you get a D of 1.002. And that's nice. The mean is great. The sample mean equals the mean of the distribution. But this might not be quite great. So if I go to look at the probability of calls answered within 120 seconds, your data set was how long it takes a call to be answered. That probability is 99% if I fit a D equals 1.002 to the distribution. But in your data, if you remember, does anybody remember in your data what was the empiric estimate of the probability a call was answered within 120 seconds? 96%. Okay, good. That was a while ago, so yeah, it was about 96%. So that suggests that even though I might be fitting the mean well, I don't seem to be fitting this tail that well. So that inspires me, if I really care about getting these outlier observations probabilities right, I need to fit this tail better, and that comes down to getting D correct. So how do I get D correct? D correct is where the maximum likelihood estimate comes in. And I think this is where it's probably easiest for us to go back and forth between my spreadsheet and the slides, just to make sure we're all clear with the path. So what is the overall path? The overall path of likelihood estimation is, first you have observations and you have a distribution. But you don't know, for us, we know these are the observations we see. We don't know which D, we don't know D. We know Pareto, but we don't know D. So we need to know which D is most likely to have generated the observations from this data set. Is that good? How do I get this likelihood function? Well, what I do is think about this PDF and think about me saying that, like, you know, over here, this large observation is much likelier under this lower D value than under this higher D value. That suggests that the PDF is saying something about the likelihood of seeing the observations I've actually observed in the data set. So I'm going to try, I don't know what the right D is, but I'm going to try for different values of this D, i.e. different curves here that I've plotted. I'm going to just plug the observations I've seen into those functions, and I'm gonna see which function gives me the sort of best result. So here's my likelihood function. If you look over at the Excel file, what are these observations? X1, X2, X1000, this is what I have in column B. It's representing my answer times. Right? So X1 is 1.24, X2 is 24.24, etc. Good? I'm going to pick on you, Brian, because you're looking, you have a stare. So that's good.
That's fair.
Sorry, I'm confused. Why are we multiplying them together?
Okay, so you're multiplying them together because you don't want the likelihood of one observation, you want the likelihood of the entire data set. And we're assuming that each of these observations was generated independently. So that suggests that if I want the likelihood of the whole data set, I'm not just going to focus on one. I need to multiply the likelihood of having seen every single observation. So I'm multiplying them together, and if you look at the Excel, what am I doing? Basically, column K is saying D equals 0.1. For D equals 0.1, I've got 1,000 observations, and each row in column D is corresponding to me evaluating this observation. So this is the first observation. Let's look at this. The first observation is 1.24. So I'm evaluating that first observation when D equals 0.1. So that is exactly this term. You can look. Why is it times 10? Because I'm getting into small numbers. And if you look at, so when I multiply these small numbers together, I'm going to get a very small number. And if you think about where the maximum occurs, it is not affected by multiplying by a constant. It's only the relative magnitudes that matter.
How come in this case we don't take the log and add it and maximize that? Like
you could. That would, in fact, the standard way to do this is to take the log and maximize that. But I was feeling like there was enough not sureness about what we were doing that I thought, let's first just see this way. If you want to take the log and maximize that, that is a standard way of doing it that gives you exactly the same answer. Okay, so we're okay that basically column K is formulating this product, column K is each term in this product for D equals 0.1, which means that if I go over here to cell G7, I'm getting my likelihood function, this is just a product, I'm multiplying everything together, so I'm getting the likelihood function evaluated when D equals 0.1. Is that good?
You have Kaiser.
And if I go down to D equals 0.2, I'm multiplying every term in column L together, which means I'm getting my likelihood function when D equals 0.2. So this is basically the likelihood of D equal is 0.1 for observing the data that I observed. This is for D equals 0.2. It says, which D do I want to choose?
I'm sorry to hear this. Oh my God.
The one that's most likely, what does that correspond to? 0.7, I heard 0.7. And why are you saying 0.7? It's, if you look at this plot, we're looking for the value of D that maximizes this likelihood function. So we're looking for the value of D that maximizes the data that I actually observed. Yes, these values are very small. The magnitude doesn't matter. All I care about is the relative magnitude. So I care about where the peak occurs. The magnitude isn't actually giving me much information. It's just that I care about where that peak occurs. And that's why it's fine to take the log. That's why it's fine to multiply by constants. Because I don't care about the value. I just care about where the peak occurs. So do you feel comfortable that what was this kind of procedure, this maximum likelihood procedure? You take your data, for every piece of your data, you insert it into your PDF function. You multiply stuff together, and you find the parameter, in this case D, that maximizes it. And why do we care about the D? We care about the D because we really wanting to get those outlier observations correct. So let me take a pause. Is that can I go is going between the slide and what's in the Excel sheet working for you? Okay. So then we should kind of check ourselves. So if I said D should be 0.7 and that's better than our first estimate, is it better than our first estimate? Well, if we do this same thing, calculate this probability that a call is answered within 120 seconds, so if D is 0.7, it's 96.5%. That's really a lot closer. Okay. So what I gained by optimizing D, rather than just setting a sample mean, is I gained a lot better precision over what's happening out in that tail in those outlier observations. Do I have the same mean? So I've got good control over this tail, right? I hope I've convinced you right now that what we've done is giving me a good fit for how these how often these outlier observations are coming up, at least according to this data set. Do I have the sample mean of that data set fit to the mean of this distribution? Well, what is D over D minus 1? D over D minus 1 is the mean of this distribution. So what is it when D equals 0.7? Yeah, so I see some confused faces and negative, and so actually it doesn't exist. So I mean, we can't have negative values in what I gave you. Everything has to be greater than or equal to 1. So what happens when D is less than 1 is you actually don't have a mean. So I've given you a distribution here that does not have a mean. So first observation is, whoa, that's kind of a mind-blowing thing. Can I actually have a distribution that doesn't have a mean? Yes, you can. This is an example of one. What's happening there? The reason you don't have a mean for this distribution is there's basically enough outlier observations that when you kind of average over outlier observations, they're giving you an infinite answer when you get that mean. What does it mean for trying to fit this distribution to the data that you actually have? Will you ever have a data set that has an infinite mean, that doesn't have a mean? No, I can't imagine it. No matter what data set you have, no matter how many outliers you have in there, you may get a really large mean, but you are always going to have a finite number. So this suggests something really sort of subtle that's going on when you want to care about outlier observations, which is the mean of your data set can potentially be a misleading signal. Because really we're getting a distribution fit here where actually the mean, the reason you're getting these really large means is it's like really, really, really large. It's like infinitely large.
Just to clarify, it's only for data sets that can only be positive, right?
Oh, yeah, that's true.
Okay, so.
No, even if negative,
So like
you're always going to have a mean, even if you have negative.
But if a data set can have negative values and D is less than 1, then that could just be the mean.
The Pareto distribution
It's
is a
always-
positive
right,
distribution.
That makes sense, because it's making up
Yeah.
parts of something.
Yeah, so if what I said about the Pareto and D being less than 1 meaning there's an infinite mean, it is always a positive distribution. Okay, so this is actually something, so there's kind of a little, I don't know, mind-blowing thing to think about. And it potentially is going to come up a little bit later in the class when we sort of talk about the stock prices, so you can kind of file this away for, I don't know, about an hour from now.
So even if we get a mean that's positive, but it's pretty small, we still argue that it doesn't have any meaning because it's
So when you get a sample mean that's small, so a mean from a data set that's small,
yeah, that's really small. We still argue that it's
probably what's going to happen is you're going to be having a larger mean when you have outliers. Because when you have outliers and you want to put a good weight on them, they are dragging your mean upwards. So it would if you have a data set and it has kind of a small mean and maybe a few outliers, it's probably not enough to say the D is less than 1 when you fit the Pareto. I can't.
I was just asking if like the sampling of the Pareto is really, really small.
Oh. The sample mean of the Pareto is D over D minus 1. So the sample mean of the Pareto can never be less than 1 because 1 is the minimum lower bound on the observations. And if you notice, when we tried to fit that data with the 606 mean, we got a D that was as close to 1 as possible. So from that perspective, when we tried to fit the sample mean of the data, it was telling us that the mean was sort of as small as could possibly be, which is kind of an indication that something is weird. Sorry, the D was as small as could possibly be. I said that wrong. When we tried to fit the D using the sample mean, we got an indication that D was as close to 1 as it could be. It was very close to 1, and we know 1 is the boundary line over having a mean versus not having a mean. So when you get a D that's fitting close to 1, that suggests that maybe you really want to be putting more weight on the outlier observations. Did that answer the question to both of you?
How do you
How do I interpret a positive sample mean?
Yeah.
The way I interpret the mean for the Pareto is the same as I interpret the mean for any other distribution. I'm clearly missing something in the question here. Can anyone help me out?
Yeah.
Okay, so I'm going to move on. I'm happy to talk to you after class. I obviously missed something in your question. The ultimate punchline that I wanted to get there was Pareto is very interesting distribution. You're really interested in this parameter D that controls the tail and how often you're going to see outliers, and it is possible to get a D where the distribution actually ends up having an infinite mean because there's so much weight on, you have so many large values, potentially. Or few very, very, very large values, is what I'm saying. Okay, so let's see. So excitement about Pareto is hopefully at its peak. I'm going to take a small pause. It's peak, it's minimum, it's we're on the downhill now. So I'm going to take a small pause. So put your name tags away. I'm pretty sure I'm not going to get this perfect, so let me just like set the expectations away, but I'm going to try. So Byron, Jesse, Rue, JP, James, back to you, I know you, Andrew, Wynn, Hassan, Adam, Paige, Dan, Zona, Arkar, Susie, Patricia, Sherry, Frankie, Alex, Louie, iMac or Ian?
Yeah.
I even got the nickname, right?
It wasn't a nickname.
Nice.
Now
It's a nickname now. Get him on back.
Hard, you were iMac.
Did I?
I like
don't
it.
know. Maybe it was.
Maybe I made that up. I've been wondering that for like 3 weeks.
That's fantastic.
That's pretty good, yeah.
We're all gonna call you that.
Yeah.
Wow.
You're just gonna own it, bud.
It's really bad.
Mike, Borum, Garrett, Mike, Savisha, Joe, Balaji, which I might not be pronouncing right. I'm going to skip over you. Rebecca, Lays. Lays. Brian or Binu.
Good money.
Nikki, and yeah. Yeah. Good. Okay. Okay, so now we're all excited to do log normal model.
How many more classes do you have to do this in?
Okay, so
You have so many classes.
Or do you have
but
any?
it took me like several weeks. But
Okay.
OMC, you're gonna test me again just to make sure that it doesn't.
Do you have a bunch of classes you have to memorize? Like how many students do you have to memorize?
Oh, 2, I have 2.
Oh, good, okay.
That makes it less impressive. I
That's-
No, it's.
No, it's very impressive. Very-
So log normal model for stock prices, and I want to start out and just kind of make sure we're all on the same page. Let's talk about the model a little bit. So we start out, we have S0 as your initial price. So for our homework, it was $22.80. And when we look at day 1, it's S0 times X1. X1 is my change on day 1. And if I want day 2, I've got S0 times an X1 times an X2. So this is change on day 1 times change on day 2. I could also think of X1 as equaling 1 plus the return. 3, I can keep doing this, and finally I asked you for 30 days in the future. So here is 30 days in the future. And, you know, I said X1 should follow log of X1 should follow a normal distribution, and I just said that's how it is. Why?
Because we sum them all together when we get to we're doing.
So I completely agree with you. You said I sum them all together for S30. So if I take the log of S30, I'm summing. I've got 30 terms of that sum. So that is an argument that S30 should have or the log of S30 should have a normal distribution. What about log of X1? Did I just pull that out of the blue, or is there any justification for that?
If you're generating one, basically, you're generating one X1 with a random variable, and if you just then if you generate multiple iterations of X1, all of those, according to the limit theory, should come together as a function.
I disagree with that. If I'm generating the average of a distribution,
Got it.
how well I'm generating the average of a distribution should come together. But when I'm doing a simulation, I could actually have 1,000 trials, and my histogram plot could look like anything, right?
Yeah.
Yeah. Okay, so if I was dealing with the mean, I agree, but I'm not actually dealing with the mean for X1 here. I'm talking about the full distribution. How many times does the stock price change throughout the day? A lot. Some of you finance people probably know better than I. Is it milliseconds? Is it faster than that? That's the right.
Faster.
Even faster. Okay, faster than I can keep up.
They gotta have
for sure.
computers to watch it now.
So that means instead of thinking of X1 as I'm modeling it as a normal because I just pulled out of the air and said, let's think about it as a normal, maybe another way to think about X1 is as follows. So X1 is S1 divided by S0, right? Because that's the change. That's my change over one day. But instead of thinking about that as the change in one day, let me think about that as the change. I'm going to use minutes because minutes is reasonable. Let me think about that as the change in the first minute. I'll call it S01 times the change in the second minute times the change in the third minute, and I can keep doing that until I get back to the end. I don't know that my notation is the best, but this is basically meant to be that if I think about the change from time 0 to the end of the first day, I could think about that as first I have the change in the first minute, and then I multiply that by the change in the second minute, and then by the change in the third minute, all the way to however many minutes I have throughout the day. Is that, whether or not you like my notation, that's, so I got a product. So if I take a log, I have a sum. What do you think about sums? Maybe normal. Okay, so it actually wasn't crazy for me to tell you, think about modeling X1 or log of X1 as a normal, because what I'm really thinking about is that stock price is doing a lot of changes throughout the day, and that would be consistent if we have a central limit theorem with saying normal distribution is arising. Okay, so that's that guy. And so what we end up with is this log of xi follows normal distribution with a mean and a standard deviation. And so these guys should look familiar because that's what you estimated from your data set. And if you look at the first page in my worksheet, that's doing that calculation. And my sense of the people I talked to is that was pretty fine, so I was planning not to say too much more about that unless somebody particularly wants me to. Okay, so then how are we generating this stock price 30 days into the future? We're saying, well, xi is exponential of zi. Zi should follow a normal distribution. The parameters of that normal are exactly what you estimated. And I've actually introduced the distribution on you without even telling you. It's a log normal distribution. It's kind of exactly what you think. A log normal distribution, if I take the log, I get a normal distribution. So how do I generate a sample? Well, if I want a sample of the zi, that's the normal, I'd use this norm.inverse command. If I want a sample of the xi, I take the exponential of this normal that I've generated. So if I want the stock price 30 days into the future, I'm typing, well, this was my starting stock price. This was the change over the first day equal to 1 plus the return. This was the change the second day equal to 1 plus the return. And I've got 30 days that I got to change. So I've got 30 terms in this summation. And I posted the solutions. Please don't worry if your spreadsheet doesn't look exactly the same as mine. There's certainly more than one way to do this. But for something I want to do a little bit later, it's just kind of nicer if we're all on exactly the same Excel file. So just to make sure you see how my Excel file is working, I've got Q2. And if I take, for example, row 17, day 1, day 2, day 3, day 4, day 5, I'm generating the value of the stock on each of these days by using one of these exponential times norm inverse commands. And then I do this for 30 days. And here in column D, I'm giving you the S&P 500 close after 30 days. So I have in row 17, that would be one trial of a simulation where my goal of my simulation is to give you a distribution of the S&P 500 close 30 days into the future. That good? And then you go down row D, and I've got 1,000 trials of that simulation that's giving me S&P 500 close. So I've got 1,000 different values that are possibly coming out as this S&P 500 close. And over here in column C, I'm calculating the return for each possible close. And when I say return, I'm not actually sure that return is the word I should have used, so I apologize for that, but I'm talking about the change in my portfolio value. So the ultimate change in my portfolio value is, well, it's whatever my ending value is minus $50,000, because that's the starting amount of money, divided by $50,000. Okay, so it is D17 times the number of shares I have. So it's this S&P 500 close times the number of shares I have. The number of shares I have is in column E4. And then I'm minusing 50,000 divided by 50,000. So are we good with that? I need a nod. Okay, great. Okay, so we're good with that, and that means you can calculate a mean return, you can calculate a probability that you're seeing a return above 0, you can calculate some confidence intervals on that, and you can do a histogram plot. And I kind of said in passing that, you know, if you kind of want to double check yourself, you can double check yourself for this question too. How would I double check myself for this question too? So let me do, this is, there are 2 things of dot cams in math today, so this is the last one. So let's just think about how do I double check that spreadsheet. So if D is going to represent my ending portfolio value, that is $50,000 times X1 times X2 times X30, right? It's the starting value times the change every day, and I got 30. Okay, or equivalently I could write B divided by 50,000 is X1 plus X, sorry. Okay, so no difference there. Can take the log. my page, you said originally about the normal distribution, I'm summing logs, so I'm summing logs. What should be the distribution of this side of the summation? This side of the summation, what is the distribution of this? Normal. And it's not even approximately normal, it's exactly normal, because I've told you that each of these terms are normal. And when I sum normals, I get back again a normal distribution. So this is actually exactly a normal distribution. And what are the parameters of that normal distribution?
That 0.09 number times 30 is the expected value or average?
Yeah, so the mean should be 0.029% times 30. And if we do that, that is equals, I didn't actually have that done, so it's like 2.7%, 2.78%. And what are you getting as your mean portfolio return? Something really close to that, right? And actually, let's look at this other side for a second, because I got this weird log v divided by 50,000, so why is it exactly the same? Well, think, this is exactly ln of 1 plus v minus 50,000 divided by 50,000. Agree?
Yes.
Remember I said something like 1 plus a small number when I take the log is exactly equal to the small number? Or not exactly equal, but very close. So these returns are like, they're still reasonably small, so this is actually about equal to v minus 50,000 divided by 50,000. That's your return right there. That's exactly what I asked you to calculate. So this is suggesting that when you look at this return that I asked you to calculate, or the change in the portfolio value, I should probably be calling this change in portfolio value, that should be equal to a normal distribution, and the parameters of the normal are 30 times this mean that you calculated. The standard deviation, or well, the variance is 30 times 0.425% squared. If I want the standard deviation, I take square root of that. So that's a nice little double check on what's coming out. And what did your histogram plot look like?
Normal.
Normal. Okay, so this is basically as we expected. Okay, so there's my histogram plot.
So the returns themselves aren't normal, but they're really close to normal because they're small numbers, so they're close to the log of
Yeah,
that.
yes, yes. So the returns are very close, yes. Very close to normal with that mean and that standard deviation. Okay, so I have some confidence at this point in my simulation. I've done my question 1. I have some confidence that I'm doing a reasonably good job of generating S&P because I can see that there's some match with what my theory is telling me. So now I'm ready to do something a bit harder, which is the option calculation. And any idea how I would do that one without a simulation? Okay, so that one at least seems a little bit harder to do without a simulation. We'll talk about how to double check it, but definitely it's not something you would have been able to come up with to double check it. Right? I said that a little bit wrong. From what you've seen in this class, it would have been a huge leap to come up with a way to double check. Okay, so let's think about option value. What's the problem with this advisory board's calculation? Well, there are several problems, so you can name any one you like. Yeah, first of all, they're assuming every day has the same return. That doesn't seem like what you want to do.
Doesn't take into account variance.
It doesn't take into account variance. And if I'm going to say something a little bit, I'll say fundamental. The fundamental reason here is they're sort of doing a function of an expectation. They're trying to do something to sort of say, well, I sort of expect the value of the S&P 500 index in 30 days to be this. And there's some problems with that calculation, but even if they did that correctly, that's not how the option's working, right? The option is waiting until the end of the time horizon, and sometimes you might see a value that's 2340, sometimes you might not. But if you just plug an expectation in there, you just plug an expectation in here, it's either going to be above 2340 or it's not, period. There's gonna be no distribution. And if, okay, so first of all, let's make sure we're all on the same page with how the option works, because I got some questions about that. So I pay $4 at the beginning of the time horizon, and that's it. My $4 is gone. I don't see it again. Okay, at the end of 30 days, I look at the value of that S&P 500 index. That's S30. And if it's above 2340, I have this right to buy the stock at 2340. So if the index is above 2340, I get to buy the stock at 2340 and sell it at whatever it's at, and I will make a profit. Actually, I will only make a profit if this is at least is more than 2344 because I've already paid $4 for the option and that's gone. And if it ends up that the S&P 500 is less than 2340, I don't want to do anything with this because all I'm going to do is lose more money. I've already lost my $4. That was enough. Okay, so we know how to simulate this S30. From that, I can determine the distribution of this option value. So let's go for a second to my spreadsheet Q3 option. And what's happening there, if you look at column E, column F, we've already decided we know how to simulate S&P 500 close. So for each trial in this simulation, and some of you that talked to me, I said, oh, think app shop case, right? So this is similar to app shop case because this is like the savings. The S&P 500 close is like the savings, but we didn't care about the savings, we cared about the present value of the winning bidder's share. So we had to translate a value from the savings distribution to present value of winning bidder's share. Here we have to translate the value of the S&P close to what that means for the option. And so in column E, I'm translating a value of the S&P close to what it means for the option, and in particular, I'm making this calculation. So you can look at my E, and I'm just doing, okay, so that is the maximum of 0, and F18 minus 2340. And now if I look down column E, I have a distribution of option values. Sometimes they're 0, sometimes they're a lot more. And tell me some observations you made when you were doing this. What did you think about buying this option? What happened to your portfolio, Louis?
Well, when I did it, I started getting like crazy numbers of what the fund could be worth, and the options being worth much more than 531 that they gave as an example for the expected value. So at first glance it became very tempting, but then you start to notice that when I talked to you afterwards, like that a lot of the times the option is not worth anything anymore because of running a simulation.
Yeah.
Yeah, I found something very, very similar. One thing I noticed is that basically because you're buying so many more options than you would be able to buy shares outright at this price, the advantage, so for every dollar you make on the option, or in the market, you make about $570 if you were to invest all the money in options instead. So the payoff can be ridiculously high, and it's like, honestly, if you're managing $50,000 for a fund, if it's the USC endowment, you spend $50,000 going to the bathroom, it's pretty incredible.
So both of you have noted this observation, the payoff can be really high. That's really attractive, right? That part is really attractive.
But you can also get 0.
But you can also get 0.
Yeah.
So what was your mean return?
300.
Something like 500%. You got a really high mean return, which is accounting for what you just said, right? Sometimes it's really... And how often did you just lose all your money? Like 50%. And yeah, so let's pause with that observation, and then we'll go back to what we actually wanted to do with the portfolio. But that's exactly the observation, which is basically, you go to the histogram plot of your option, which I can't find, but there it is. It's very skewed, right? There's a lot of time you are losing all of your money, but there's some huge returns you're seeing here. And I think this is also a good time to, you've heard of Black-Scholes formula? So you actually have just figured out the Black-Scholes formula in your simulation, and I thought maybe it'd be be nice to show you that. And you know, it's not that I'm just having you do simulations of stuff I already know. This simulation, once we sort of see it coincides with Black-Scholes, it also gives you an idea of how to price any kind of option, and there's a lot of them that we don't have formula for, so. But let's just first see, how do we connect with Black-Scholes here? Okay, so what does the Black-Scholes formula say? I realize this is like a lot of math, but if you think about what it's trying to do, it's kind of amazing, right? It does say I can enter an equation into the Excel file and come back with what an option should be priced at 30 days into the future. So let's just try to parse this for a second. So this guy here is the mean value of the option. And what are my different numbers? So X is the strike price. For us, that's $23.40. That is, you are allowed to buy this stock 30 days into the future at $23.40. $23.40 is your strike price. The ST is this unknown ending price. To calculate this, what do I have to know? I have to know the initial price of the stock. That's the S0. I have to know T. T is the time horizon. So for us, it's 30 days in the future. I have to know mu, which is the one period drift, which is what we calculated as 0.0925%. I have to know sigma, or sigma squared, the one period standard deviation, which we calculate as 0.425%. And that's everything I have to know. The X is the strike price, I already said that. So if you look at the right-hand side of this formula, it's dependent on your initial price. It's dependent on your drift. They call it the drift, the one period mean. It's dependent on your volatility, this one period standard deviation or variance. I use variance here, technically that's standard deviation and square is variance. It's dependent on your time horizon. So there's like 5 numbers there: time horizon, starting price, strike price, mean, volatility that I care about. Now let's go to the Excel file for a second. And I went ahead and I programmed this in for you because I thought that even though that is so beautiful, it might be a lot to like put in the Excel yourself. So go to my spreadsheet. I mean, you could all do it. It's just that it might take more than like 5 minutes to sort of get it right. So if you go to Q3 option and you look at column G and H, go ahead and look at column G and H, and the yellow is input to Black-Scholes. So the input to Black-Scholes, this is our starting price, S0, 2280.85. Our strike, 2340. Our time horizon, 30 days. Our mean that we estimated, 9.29%. Our standard deviation that we estimated. This intermediate was just for me to make sure I type things in right. Intermediate is equal to this term right here, ln S0 divided by x plus t mu divided by sigma square root of t, because I always get worried when I'm typing in long formulas. And this option value is then equal to this entire right-hand side of the equation. So if you kind of parse what I'm doing here, I got an exponential, I got a norm.s dist, and I'm just kind of getting the right parameters in the right parentheses. You can observe that this is 24.84. Can somebody now take the average of column E for me? The average of that option value for just one option? And tell me what they get?
25.
25, that's pretty dang close. And let's do it with the confidence intervals too. So let's take a confidence interval, let's do 25 and give me the lower and upper end of the confidence interval. So I'm doing equals average of, option value, there we go, column E, minus, I'm going to do 95% confidence interval, so 1.96 times standard deviation of column E. And I have 1,000 trials, so 1,000 observations, so square root of 1,000, not 100, 1,000. And then I'm going to do the upper end, so this is equals average. And you guys might as well, I'm counting on you doing this along with me. You may be faster. And plus 1.96 times standard deviation observations. Okay, and so let's observe that our confidence interval exactly straddles that value. Press F9 a few times. And basically 95% of the time that confidence interval should straddle your option value. We know this one is exactly correct. This one is exactly correct. This should give you a high degree of confidence if you've got a nice simulation going here. And you're doing a pretty good job of estimating your option value. And if you think that interval length is too long, do a few more trials and you can get it down exactly. Do 100,000 trials. Okay, so is this clear, relationship between Black-Scholes and your simulation? Nod. Okay, good. Joe, thank you. Okay, so what if you wanted to determine the value of a more exotic option? Why do we need to stick with this thing? There's so many exotic options out there, I don't even know most of them, I'm sure. What do I mean by exotic option? So you can think of anything you want in your head. There's gazillions. They're still being come up with, is that a word? Some of them are sample path dependent. And I think one thing that's interesting about the specific way I constructed this simulation, or we did construct this simulation, is you know the value of the stock price on every day, right? For each of these trials. So some options depend on the path the stock price takes. For example, this one that I've constructed is, what if my payoff was based on the minimum price seen over the time horizon? So 2340 is still my strike, but instead of looking at S30, the price in 30 days, I'm going to say you only get a payoff if the minimum price over the next 30 days is above 2340. I have absolutely no idea how to value that. There's no Black-Scholes for that. But there are people constructing Asian options and exotic options, and you can think of other weird payoff functions you want to construct. How would we figure this out? How would we figure out the worth of this option? I claim it's a one-line change in our simulation.
You just, instead of the price, the 30 price in that minus 2340, you just make that segment of all those days.
Yeah. So look at your option value column E. This suggests that my option value column E, well, instead of F18 was my ending price. I'm going to substitute in a minimum of the price I've seen over the last 30 days. Or if I want to do something else, if I want to construct some other weird option, do whatever you want in your head, and over here in column E, you're just going to translate between either the ending price or the price you've seen over the next 30 days, or the maximum between halfway through and the total ending value. Or some of these, I think they're Asian options, maybe somebody can correct me, are based on an average value seen over the next 30 days. There's all kinds of things you can come up with. And this is one way to value them. And there's no analytic formula for most of them. So.
I have a question about how options work. So the strike price isn't like your personal strike price, I wouldn't sell it, but it's like when you buy the option, it's like contractual, you're not allowed to sell unless this is the price.
No, it's completely your decision.
So then what is this minimum? Is that just like up to you? Like, oh, for me, my option? Oh wait, never mind. I'm sorry.
It's so the American option, I believe, you can purchase it any time before the end expiration.
Yeah.
So this is the idea that if you want to wait until they hit a certain point and then purchase it right then.
Okay, so this is like trying to see like, oh, what do I think the minimum will be, and when it gets close to that, that's when you buy it.
No, you have to buy the option, for this one, you have to buy it at the beginning of the 30 days. This is one I constructed out of my head. So this isn't like corresponding to something you'll go to the Wall Street.
Like if this was an option, what would it mean?
It would mean that at the beginning of 0 days, I pay $5. I have the ability to purchase the stock at price $23.40, 30 days in the future.
Okay.
And the amount I'm going to pay you back depends on the minimum stock price value I've seen over the next 30 days. So the payoff I'm going to return to you is not based on the ending value I see, it's based on the minimum that is seen over the next 30 days.
Okay.
So in this case, it would be an option that I do not allow you to exercise until the end of the time horizon. And then we would compare these two.
So you buy the option for $4 or $5 or whatever, and the strike price is $23.40, but instead of the ending price minus $23.40, what you're paying to me, it's like the minimum over those 4 days.
Yes.
The difference, okay.
Yeah, that's not something you're gonna see in the Wall Street Journal and see. I just wanted to do an illustration of the fact that once you see how to value this quote plain vanilla option, you can value sort of something crazier that you construct in your head. And that is something that like some of these finance firms do, is they try to put out new financial derivative products. And one of the ways they might try to value them is through a simulation. So we're a little bit rudimentary in our simulation, but it's, and I say rudimentary because we're doing log normal model, just to clarify. We'll talk about it in a second. Okay, so overall point is you know how to value several different options. And now let's get back to your recommendation. So this goes back to JP and Louis' observations, which is, okay, so I want, option is giving me a super high return, but there's probability of losing money. And of course, if I'm USC and I say, $50,000, what's our endowment at? Is it 4 billion?
3.6 billion.
3.6 billion, you know. That's like epsilon. That's like me buying a latte in the morning. But, you know. On the other hand, if we're a smaller investment club and $50,000 is important to us, maybe it's not quite like that. So what's your recommendation? Yeah.
So one thing I noticed when I was kind of running my simulation is that once you put pretty much any amount of, so I basically ran it so kind of your risk of losing money if you put 0, 10, 20, etc. percent of the money in options versus stock. The really interesting thing was your risk of losing some amount of money is basically the same between like 2 or 3% and 100%. So if you're worried about losing money, you should, if at all, you should probably just not put any of your money in options. But if you're willing to lose some amount of money, you can basically put somewhere between 30 and 80% and still not lose everything.
But it's not just like the percentage chance of losing money, right? It's also
the amount of
magnitude,
loss. So
right?
yeah, it's also one thing like kind of in my simulation. Sorry, I'm just going over to it. So one thing I found was basically that the average the average loss if you, or the average, I also did like average marginal loss if you invested all of it in options. And it's basically like if you invest about like if you invest somewhere between 30 and 80% of it, you'll still keep some of the money basically.
Yeah, I guess I was trying to look for, I was trying to see if there was almost like we do with MLE to see if there's a place where you can see when we had a higher mean return but a lower standard deviation. So I didn't really know how to graph it correctly to get like a maximum.
So this is exactly what I'm looking at. There's not one right answer. The observation is that there's a bit of a trade-off between this mean return and probability of losing money. And kind of what you observed, JP, I observed too, which is like, maybe it's not probability of losing any money I should focus on, but probability of losing like, maybe more than like 5%, something like that. Because if I focus on probability of losing more than 5% and I think of different portfolio combinations, it doesn't have to be 5%. This is just illustrative of what Balaji and JP are talking about. Is I can plot some kind of graph that's kind of like a risk return. And on the x-axis here, so I have the probability of losing more than 5%, which if I put everything in the S&P 500 fund is basically 1. I'm not going to lose more than 5%. On the other hand, if I put everything in the options, I've got a reasonable probability of losing more than 5%, because I might lose everything, right? And then I can obtain, by splitting the proportion somewhere between the index fund and the stock, I can obtain sort of an efficient frontier. I think that's what you're kind of going for, Balaji. That sort of tells me what's the trade-off between the probability of losing money and how much return I have. And I don't get to like, there's not going to be like a minimum there. It's really like a, what's your risk-reward appetite? So if you're willing to have more risk, you can get a higher mean return. But there's no way of like circumventing that. Okay. So that's kind of what I was thinking, and I say one possible way to evaluate is because I'm kind of thinking you to get about what's this risk-return analysis. There's no right answer for where you want to be, but there's sort of a curve you can construct, and that can drive a little bit how you want to balance between stock and options.
Is the x-axis the chance that you'll lose?
More than 5%.
More than 5%. Okay, right. And then, is there a way to model this, like make a formula without just like making each one like 1%, 99%, so it's like more continuous, I guess?
Oh, so, yeah, so I did it in discrete points. Doing it by simulation, no, there's not a formula. You have to do the simulations for the other ones. In general, if I'm thinking about portfolio stocks, yes, we can do a formula based on sort of mean and standard deviation. But for this one, since we're all doing it through simulations, I can't do it as a formula. I just did it as numerically generating this one. And it's coming from doing several different simulations with several different splits between the option and the index fund. Okay, so at this point, you're kind of thinking, okay, so I know basically everything there is to know about this log normal model. This is like the third day we've said something about it in class. We spent a lot of time on it. This is like this, okay, I know ins and outs of this model. What don't I like about it now that we've done everything? Now that we've talked about it so much? Maybe the first thing I could ask is kind of in question 4. How did you feel about how well that model fit to your data? I'm going to ask for, let's see, somebody besides JP, and somebody without a name tag. So, how about Gorm?
Wait, sorry, I didn't.
How did you feel about I'm sorry, I put you on the spot, which wasn't fair. But how did you feel about the log normal model versus the data you were seeing? Did you like this model? Did you feel like it was kind of a toy model? Is it?
I found that in reality, the stock value has more rare events, like extreme values, but this model is just focused, the data is focused on the mean.
I completely agree with you there. And is there any way I could see that? Based on some of the techniques we've used? Anybody do like a QQ plot? Yeah, so if you kind of look at a QQ plot, one thing you will observe is that the normal fits pretty good. I'm pretty close to a straight line, but what Borum said is exactly correct. I don't actually have any large observations. I don't really get any outlier observations, and so that kind of says I don't really know what's going on out in the tails. I don't have data to tell me that, and that would be a big worry, right? So that's one, and let's come back to that criticism in a second. There's another one. What's another criticism? The model was derived from the CLT, right? Were the returns in your data, were they independent?
No.
Yeah, no. So if you looked at a leg plot, it wasn't terrible, but you do a Q4. So what am I doing? I'm looking at in column D, so I've got the returns in column C and column D, I'm just lagging it by 1. And if you look at the plot, well, I can't really tell too much from the plot, but if I look at the correlation, it's a negative 13% correlation. So that is not independent. So there's one worry that you can see in the data that's not kind of quite right. And actually, let me go back to the first worry. I'm back here, going back and forth. And Borum, you said this great observation is that I don't know about these outliers. Can we connect that to the Pareto distribution in the beginning of class? What is the entire log normal based on? The entire theoretical underpinning of it?
Basically, I get it. All those returns are in some way, shape, or form reflective of what the future's going to look like.
That's one thing.
something like a scandal or something could happen to this particular, or some kind of disruptive event could happen that disrupts the entire thing that couldn't be predicted.
Definitely agree, so that's giving me more weight for the outliers. But I mean, when I developed the model theoretically, right, not looking at the data, there was a major assumption that got me to say x1 is normally distributed, or x30, log of x30 is normally distributed.
Kind of cheating because I'm looking at the slide, but the way we constructed it was that all of the returns were independent, and like that's likely not true. Like the return from yesterday probably has something like an influence on what's happening today, and the normal distribution assumes independence of the variables.
So actually, more specifically, the CLT assumes independence.
Right.
And I completely agree with you, but I'm not as worried about that because there are forms of CLTs that are weaker that allow for some dependence. And you and I can debate over, is negative 13% large enough that it completely kills my CLT, or, you know, I would say it's a little bit borderline. I don't actually know the answer to that question. It's worrisome, but it's not quite as fundamentally worrisome as what I'm thinking about.
Maybe like when we did the average return, we got that like 500% number.
I just gave the hint, CLT.
So when we do CLT, we assume normal distribution, so there's tails, but maybe.
Okay, so CLT tells me the sum is normal, right? I'm telling you x30 or something like that. I'm saying the sum is normal. Does a normal have a mean?
Yes.
Normal has a mean. I said we were trying to connect this at the beginning of class. Pareto distribution. Did we see a Pareto that doesn't have a mean? If you have a distribution that doesn't have a mean, can you have a CLT? Okay, here's an even more like fundamental thing that completely blows the whole thing up. The underpinning of the entire model is that we have a CLT in activation, a CLT that's working. One thing that could kill that is dependence. Another thing that could kill that is tails. Your tails are so heavy that you don't even have a mean of your underlying distribution. How do you possibly develop a normal CLT? I have no idea. Okay, so that's the other thing that would completely kill this. And what's the consequence here? So if we don't accept the log normal model, what does this mean about deciding whether or not to purchase an option with a strike price at say $2,500? So presumably at much lower price than $4. But under the log normal model, if I look at the number of observations in my simulation that are more than 2,500, it's like 3. So I probably wouldn't. But what happens if we go and we say, you know, this really shouldn't be log normal model. We need a model that accounts for these outlier observations better. Am I more or less likely to purchase that option?
More likely.
More. Because the problem is the log normal will be underweighting the fact that I might get these tail observations, and that would cause misleading calculations about option prices and option values. Okay, so that's, that's this last question we already talked about. Okay, so then what have we learned? So we've gone over Pareto distribution, we've gone over log normal distribution a lot. Next time I want to review a little bit, so what's going on next week? I should say something about a week from today. You have an exam. It's basically an in-class exercise. There are 2 things. There'll be one part on some kind of stock price option, something, I don't know what, but something around that. There'll be something on, I'll give you a data set and I'll ask you what is the right distribution, and I'll put some hopefully semi-interesting story around it. So that's what you're looking at. It's open everything. Computer, the intention is it's like when you're working, you have access to everything you need, internet, notes, all of that. No neighbor, that's the rule. Is that any questions about just kind of in general what's happening there? Okay, then I wanted to leave, so you should have a link for doing evaluations, and I'd really appreciate it if you take the time to do that. So I wanted to end just a little bit early and let you fill out the evaluations, and yeah. And so I'm going to